Simple circuits. What is potential difference or voltage? When there is a current I passing through a resistor R from point X to point Y, we say the voltage or the potential difference across the resistor is VR or Vxy equal to IR, where Vxy is called potential difference. And since current flows through a resistor from higher electric potential to lower electric potential, in the diagram, the electric potential at X is Vx and that at Y is Vy. And potential difference Vxy equal to Vx minus Vy. Example, if resistance is 10 ohm and the current is 2 amp, then the potential difference across the resistor is equal to 2 times 10, which is 20 volt. That means the potential difference, or we say the potential at X minus the potential at Y would be equal to 20 volt. Or we say the potential at X is higher than the potential at Y by 20 volt. If point Y is earthed, the electric potential at Y would become 0. That means if Y is earthed, Vy equal to 0. In this case, Vx would become 20 volt. Example 1. First case, potential difference across xy, Vxy equal to IR, which is 1 times 6 equal to 6 volt. That means potential X minus potential Y equal to 6 volts. Since Y is earthed, therefore we have Vy equal to 0. Hence, Vx equal to 6 volts. In the second case, we have potential difference across xy is Vxy equal to IR 1 times 6 equal to 6 volt. That means Vx minus Vy equal to 6. Now, since X is earthed, that means we have V at X equal to 0. The potential at X is 0. Since Vx is 0, therefore we have potential at Y becomes negative 6 volt. For the last case, since the current flows through the resistor from Y to X, therefore we have potential difference now across Yx is equal to IR, which is 2 times 5 equal to 10 volts. In this case, we have potential at Y minus potential at X equal to 10 volts. Since point X is earthed, that means potential at X becomes 0. Therefore, potential at Y equal to 10 volt. internal resistance of a power supply can be represented by the symbol with smaller letter R. For an ideal power supply, for example a battery with EMF E, the internal resistance is assumed to be 0. In this case, the terminal voltage across the battery V xy is equal to the EMF of the battery. That means if we use a voltmeter to measure the voltage across the battery, the voltmeter reading would become the EMF of the battery. However, if the power supply or the battery is not ideal, or we say this is a practical power supply, then there is internal resistance inside the battery of EMF E. The internal resistance can be written in the form of R. The internal resistance can be represented by drawing a resistor of resistance R inside between X and Y. If this is an open circuit, that means there is no current flowing through the circuit. Then the voltage across XY is still equal to the EMF of the source. When a voltmeter is applied across XY, then the voltmeter reading will still be equal to E. However, if this is a closed circuit, there will be current drawn from the battery. In this case, the potential difference across XY would be equal to EMF of the battery minus the potential difference across the internal resistance, which is I times R. Therefore, we have V across XY equal to E minus IR, which means the voltage across XY will be smaller than the EMF of the battery. If now a voltmeter is applied across XY, then the voltmeter reading will become E minus IR. Example 2. Terminal voltage across the battery V is equal to the EMF of the battery minus the current times the internal resistance of the battery. For case 1, since both I and R are equal to 0, then terminal voltage across the battery equal to EMF of the battery equal to 3 volts. For the second case, since current equal to 0, therefore terminal voltage across the battery equal to E, still equal to 3 volts. For case 3, since I is 1 amp and internal resistance is 1 ohm, therefore terminal voltage across the battery equal to E minus IR equal to 3 minus 1 times 1, which is equal to 2 volts. Notice that when there is a current drawn from the battery, the terminal voltage across the battery should be smaller than the EMF of the battery. This must be true when there is current. When there is low internal resistance or there is low current, the terminal voltage across the battery will be equal to E, MF of the battery, by V equal to E minus IR. Case 1, we have 6 equal to E, since I and R are both equal to 0. For case 2, V equal to E minus IR. The terminal voltage is the reading of the voltmeter reading, which is 2 equal to EMF 3 minus current 0.5 R. Therefore, internal resistance of the battery is 2 ohms. Case 3, V equal to E minus IR. V is 4 equal to E is 9 minus I. Internal resistance is 2 ohms. Therefore, the current drawn from the battery equal to 2.5 amperes. Experiment to find the internal resistance of a battery. Connect the setup as shown in the diagram. The procedures are: first, set the rheostat to a high resistance R. Next, close the switch and record the ammeter reading. Next, open the switch and adjust the resistance of the rheostat. Then repeat steps 2 and 3 several times. After the experiment, we obtain different sets of currents I in the circuit and different sets of readings of resistance of rheostat R. Report a graph of R against 1 over I. The graph would be a straight line. Since EMF of the battery equal to the current I in the circuit times the total resistance of the circuit, which is R plus the internal resistance of the battery. We arrange the terms, we get R equal to E over I minus R. The graph shows that the slope of the graph is equal to the EMF of the battery, while the negative intercept represents negative of the internal resistance. For example, if the y-intercept is equal to negative 1.5 ohms, that means the internal resistance of the battery R is equal to 1.5 ohms.